Hello students, this is lecture number 5 of Signal and System course, and in this lecture we are going to discuss about signal energy and signal power. And this is my contact information, my email address. If you have any queries regarding this lecture or regarding this course, you can send me an email anytime. So in signal processing, the term size of a signal is quite oftenly used to represent the strength of the signal. It is crucial to know the size of a signal used in certain application. For example, you want to compare the energy consumption of two devices. For example, LCD screen of your computer and the CRT screen of your computer. And if you want to compare the energy consumption, you will compute the size of the signal in both cases, and then you can actually quantify the energy consumption of the two devices. Signal size can be measured in many ways. For example, peak absolute value, average absolute value, RMS value, and many other ways. For example, the area under the signal is a good measure of describing the size of a signal. Right? However, computing the area under the curve of a signal may give you wrong result, because some signals, like sinusoidal waveform or the one that is shown in this figure, has positive and negative parts. So when you compute the area under the part A of the signal, you will get positive area, and when you will compute the area under the curve of part B of the signal, you get negative area. And when you sum both these together, you will get a smaller area, which one represents the strength of this signal. And likewise, a sinusoidal waveform has a positive cycle and equally of exactly same negative cycle. And because of this, the positive and negative cycle would fully cancel each other. So whenever the signals have positive and negative peaks, then they either cancel each other partially, or cancel each other completely and won't give you anything. So this cannot be used as a measure of strength. In order to solve this signal, we can actually first compute the square of the signal and then find the area under the curve. Right? In that way, you will find the correct strength of the signal. So when you take the square of the signal, the negative part will be converted into the positive sign, and the area under the curve then can be added together to find out the energy content in the signal. You can see here, when we will compute the square of the signal, you see a negative peak would be converted into positive, and now you can actually apply the integral or compute the area under the curve and to find out energy of the signal. Now here you can see a modulus operator is used. Modulus operator actually generalize the square of the signal. When the signal is real, you can simply take square of the signal, but sometimes the signals are complex, right? Complex exponentials. They are complex signals, and in that case we have to first find out the modulus of the signal and then take the square. So the signal energy actually shows the strength of the signal, and it doesn't have any specific unit, but actually the physical signal that it represents, same unit can be used for that. For example, if it represents the voltage signal, or if it represents the current signal, or if it represents the temperature signal, same unit will be used for signal energy. It is the concept of energy carried in a signal irrespective of the system. It's not it's independent of the system. It is just the energy content. All physical activities are mediated by transfer of energy, and the systems which are excited by signals, whether they are carried by the wire or they are carried by the wireless medium or the optical medium, whatever, they carry the physical energy and they excite the system. They are applied as an input to the system, and system actually responds according to the energy content in the signal. So if x of t is the signal and we want to compute the energy of that signal, which is represented by E of x, then it can be calculated using this integral. Ex would be equal to integral of x square from minus infinity to infinity when x of t is real. And if x of t is complex, then first we have to find out the modulus of x of t, and then find out the square of that, and then find out the integral modulus square of x of t from minus infinity to infinity. Now signal energy must be finite if you want to meaningfully measure the size of the signal. If it is infinite, it won't give you any indication or give you any idea about the strength of the signal. Now sometimes it can be infinite, and what is the condition when the signal energy would be infinite? Obviously the condition where the amplitude of x of t is not converging to 0 when time reaches infinity. This happens when your signal is not time limited. It is infinite signal, like a sinusoidal waveform that can expand from minus infinity to infinity. In that case, we cannot find out the signal energy because the signal energy contents would be infinite, of course. Right? So in order to find out the energy of the signal or compute the energy of the signal, the amplitude of x of t must converge to 0 when time reaches infinity. For example, there are two signals given in this figure. In figure A, we have a function g of t which is converging to 0 when time reaches infinity. Obviously, we can compute the energy of the signal by computing the area under this curve. However, in part B of this figure, signal is not converging. It is continuously changing from minus infinity to infinity. So that we cannot compute the energy of this signal because this integral won't converge in that case. Now here is a simple example in which we need to find out the energy of the signal x of t equal to 3 e power minus t when t is greater than or equal to 0. Now in that case, first we need to find out whether it is possible to find out the energy of the signal. Can you guess? Yes, of course it is possible because it is decreasing exponential. So the amplitude of the signal would converge to 0 when time reaches infinity. If it was increasing exponential, then obviously we cannot find out the energy of that signal, right? So graphically you can see, okay, that signal starts from 3 when t equal to 0 and converges to 0 when time reaches infinity. So obviously this signal is bounded, and energy can be determined using this integral. Now you have to compute this integral x square of t and then evaluate the integral. This would give you the area, this one, area covered by this exponential, and this area basically represents the strength or size of this signal. Other examples. There are some exercise problems for you, and in each case you have to find out the energy of the signal. But let me tell you that it is not possible to find out the energy in all cases, right? So let us start with the first one. I would solve only few of those examples, let's say the A and C, and I'll leave rest of the examples to you to solve it. And if you find any difficulty, you can contact me anytime, right? So let's start with the first one, and then we'll solve the part C, right? So is the finding out the energy of unit step function. So unit step function, you know, has amplitude 1 when time is from 0 to plus infinity, and it has amplitude 0 when time is between minus infinity to 0. And graphically you can represent unit step function this is the graphical representation of unit step function, and uh, you know that the amplitude of unit step function does not decrease when time reaches infinity. It means we cannot compute the energy of this signal, and if you compute it, you may find it infinity, right? So let us substitute the values in the formula and see what happens, right? So energy formula is from integral of minus infinity to infinity, and signal is square dt. Here the value of the signal is 1, and it is 1 between 0 to infinity, and the value of signal between minus infinity to 0 is 0. Now solving it further, you will get energy equal to infinity. So this is what we expected. We know from the graph of the signal that amplitude is not converging to 0 when time reaches infinity, therefore the energy of the signal would be infinite. So you cannot say this signal is now energy. Coming to the part signal C of the exercise problem, we have to determine the energy of this signal x of t. Now in this signal we can see that the amplitude of this signal is decreasing or converging to 0 when time reaches infinity. It means it is possible to find out the energy of the signal, and it won't be infinity at least. Now in order to find out the energy of the signal, we need to first write down the mathematical expression of the signal. So in order to write down the mathematical expression, let us break the signal into two time slots. One is between minus 1 and 0, another is from 0 to infinity. Between minus 1 and 0, the signal is 2 simply, and between 0 and infinity, it is 2 e power minus t upon 2. So mathematically, we can write down the expression of the signal as x of t equal to 2 when time is between minus 1 and 0, and it is equal to 2 e power minus t upon 2 when time is between 0 to infinity. Now we can substitute these values into the energy formula and find out. The formula for computing the energy of the signal is given. Now we know that x has two values. One is when integral is between minus 1 to 0, which is 2, and when integral is from 0 to infinity, and has value 2 e power minus t upon 2. So substituting these values into this integral, we get this expression. Now solving it further, 2 square would be 4, and it is constant, would be taken out of the integral. Similarly 4 from here would also be taken out from the integral. Now evaluating it further, you will get energy equal to 8 units. And similarly you can also solve the other exercise problems that I haven't solved in this, and if you find any difficulty, again you can contact me. Now in some cases we saw that the solution of this integral is not converging, right? It is because the signal energy is infinite. It means the signal is either periodic or it doesn't end anywhere, right? Like a simple sinusoidal signal, which it starts from minus infinity to infinity. It is a periodic signal, and you cannot find out the energy of that signal, right? So in that case, you know, it is better to find out energy between specific time, right? For example, for periodic signals, find out the energy for one cycle, one complete cycle, right? So for this signal type, it is more convenient to deal with the average signal power instead of the signal energy, right? So computing the energy per unit time, right, which is called power. Now we can compute the signal power of any function which is not time limited by computing the energy of the signal for one particular time period. Let's say, for example, in this signal we have one time period from minus t upon 2 to t upon 2, and that is one complete time period t, and let us compute the energy of this signal from minus t upon 2 to t upon 2 and then divide it by t, you will get signal power. Right. So mathematically the energy, computing the energy of the signal from minus t upon 2 to t upon 2 and then dividing it by t would give you the average power. Now let us find out the average signal power for this sawtooth waveform shown in this figure. It is a periodic waveform, and in order to compute the average signal power, let us take one complete cycle, let's say from minus 1 to 1. So from minus 1 to 1, the value of t, the time period, would be equal to 2, and from minus 1 to 1, the function is basically the ramp function, unit ramp function, right? And it can be represented by t. So let us use this formula. Now 1 upon t, we know the value of t is 2, and the limit of the integral would be from minus 1 to 1, and x of t is simply equal to t, right? So substituting all these values here, we get power equal to 1 upon 2 and integral from minus 1 to 1 and t square dt. Now evaluating the integral, you get power equal to 1 upon 3. Now this would be the same result if you take any one cycle of this waveform. If you take from minus 3 to minus 1, or you know, from 1 to 3 or 3 to 5. Again, there are some exercise problems. You have to compute the average signal power. For example, this one, in this example, you have time period equal to 12, and the amplitude of the signal is basically 0, maximum value is 0.8. Again, this one, a sinusoidal waveform, which is a periodic waveform. You have to find out the signal power for this, and unit step function as well as for a unit ramp. Now the new classification can be done based on the signal energy and power content. A signal with finite signal energy is called an energy signal. A signal with infinite signal energy and finite average power is called a power signal. So whenever we refer energy signal, it means it has finite signal energy, and when we call power signal, it means it has infinite energy but it has a finite average power. Now there are some signals which are neither energy signals nor a power signal, right? So these signals, for example, a ramp function r of t equal to t, it increases with time, right? It is not bounded, and it doesn't repeat itself for any specific, right? So this signal is basically neither power signal nor energy signal. So that is end of lecture number 5. I will be uploading next lecture in the next week. In the meantime, try to solve the exercise problems of lecture number 4a, 4b and 5, and contact me via email if you find any difficulty in these lectures.